Bless you. Market equilibrium point. I'm pretty sure we actually talked about that. I think in section 7.1. Maybe that was when we talked about breaking even. Market equilibrium is when supply equals demand. Not something to memorize for this class, but just it's an application of solutions and intersections. Number 10 was no solutions. But how many of you guys figured it out up here? How many of you guys figured it out down here? Up here, do you see the slope very obviously being the same? A couple of you, yes. You're like, oh yeah, it's -3/2 for both when I get y by itself. But for others of you, you would have been like, nah, they're different equations. Let's go. And when you go, everything should have canceled. Oh, well, everything can cancel on this side. This is a false statement. Everything did not cancel on the other side. So no solutions, and if you were to graph it, you would have seen they were parallel. Truly parallel. Truly parallel. I think there's another question in homework that might have been not so truly parallel. Number 20 was consistent. There was a solution. And only one solution, -17/5. Number 34 matches with D. Of course, they give you the justification if you were to solve it. They're inconsistent, or their slopes are the same if you were to get y by itself. With rise over run. Number 46, we're trying to find that equilibrium point. Which, I mean, if you guys just guessed, maybe you would have been like, I think I'm supposed to find the intersection. Set them equal to each other. But they didn't give it to you this nicely, I don't think. Wasn't it like a P equals and a P equals, and you were having to actually like figure out what was going on? Yeah. So just in case it got a little confusing when you guys were looking at the problem itself. Where's that P equals? Crazy, I thought it was like a whole separate section. I was just kidding. I must be visualizing something else. That was given to you in a weird way. Oh, it's over here. I didn't even see it. Yeah, you had to understand the equilibrium point was when supply equals demand, but it's basically a substitution. Bless you. Or you can make it elimination by putting them on top of each other. And here in 46, you could have subtracted. The p's would have canceled to be 0. Then you would have gotten 75 minus 0.15x. And all you have to do is solve. But in context, what does this mean, this point? That we had 500 units at a price of 75. That's where that break even, wrong term, equilibrium point exists. Oh, that was it? We'll talk really quickly about that next page and why it says 7.3a and why the backboard says 7.3a. That's weird. That must indicate that there's a B. But for right now, before we move on from 7.2, was there something else that we need to talk about or see? 41 and 67. Anything else besides those two? Going once. If you guys are bored, you can be working on corrections. I'm not bored, but it doesn't apply to you. But we are going back to notes in just a second, so don't get too distracted. So 41, airplane speed. Yeah, that's a word problem. Nice thing, though, it was very similar to, I don't know if I did 42 yesterday, but I did one super similar at least. So I'm not going to take a ton of time on it, Vanessa, just because I think if you use the example from yesterday, it's kind of like a plug and chug. But let me just set it up and make sure that you're okay with that. One of the big things is that we can't have both hours and minutes. Because for our units, we want to get into miles per hour. Remember, that's the same thing as miles per hour. Because we're talking about how fast the plane is going. So the plane could be like X, how fast the plane is. The wind could be like Y. But when we're saying, hey, the wind is working against the plane, or the wind is working with the plane, depending on what part of the journey, these are like miles per hour. So then that gives us exactly what to do if we think about like chemistry and I would say physics, but most of you have it mistaken. We have miles. We have time. We have two different times because there are two different flights, the one to and the one from. Flying to Pittsburgh and then flying, flying to Arizona and then back. So if we want miles per hour, if these are miles per hour, we just need to go ahead and take the miles and take the hours it took. But there's that minutes thing. It's tricky. So I'm lazy. I would just say 3 and 36/60th and figure it out later. Because I know that there are 60 minutes in an hour. But you could also actually get like a decimal in your calculator. There's our 1800. This one's a little bit easier because it was in 3 hours flat. So we have our miles per hour here set equal to our miles per hour over here when the wind is taking or slowing down the plane or the wind is speeding up the plane. But at this point, I think this is probably what you need in order to solve. That kind of makes sense. I would add down this elimination. Super nice. Just use your calculator to get those guys. And then once you get X and once you get Y, you know how fast the plane and how fast the wind. Okay. And then 67, right? Was the other one? 67, I believe, is on the next page. Might even be on the next page. There he is. Why did I give you 67? And why is it to think about it when it's so basic and so easy? They even gave us a graph. Oh my goodness. With the graph, it's super obvious, right guys? No. Why not? Yeah, okay. Maybe do a couple of these super obvious, but to the rest of us, we will look at that and be like, oh, no solution, we're done. And then the back of the book says, yeah, good try. Because what is the difference? What is the difference? There is no difference. What? Who's this guy's slope? How steep is that slope? Go up 1 and over 100. Yeah, fair, right? But what's this guy's slope? So long story short, are they super, super similar? Yep. Are they the same? Nope. Why is that a bummer? Because they didn't just ask you whether or not there was a solution. They asked you to find the solution. But what's the dilemma if every 100 it goes up 1 and every 99 it goes up 1? And right now they're starting 4 apart. What do you have to do to your window? Fix it. Oh, wait, that's if you're using your graph. If you're not using your graph, forget that whole weird window zoom thing. We're going to have the X's go out super, super, super far. Why not just do like a, I don't know, an elimination and make your life a lot easier? Because then I know that this is going to occur, this intersection is going to occur when Y is equal to 3 -8. I don't even need to go to my calculator and worry about how nasty that zoom would be. Now what to do is plug and chug, which admittedly isn't super fun, but I would plug it into the top because when I multiply by 100, then I just add 2 zeros, 39,800. Subtract that to the other side, so negative 39,600. Then take away the negative. Ooh, someone double check me. That was a lot of that. My brain's already tired from all of this. Okay. But Vanessa, does that make sense?
199, how did that cancel out?
I got Y by itself. And then when I'm actually solving, I just subtract it. 100 minus 99 is 1. I was subtracting that. And then the X is negative X plus X. And then 200 minus negative 1. Okay, and the nice thing is, I mean, they totally, in the direction, said they appear to be parallel, but they're not. So they gave you the huge piece of information that you might have missed if you had just been given the graph. But just to be aware, some things will look to be parallel when they're really not. Even parabolas, if you zoom in enough, ooh, this is kind of like calculus now. Even parabolas, if you zoom in enough, just look like line pieces. But only if you zoom in far enough. All right, guys. Those are the only questions I heard. Oh, I'm sorry. I meant to do a last call. Last call. Go on once, twice. Oh, sorry.
Can you do
7.3?
Oh, yeah.
7. Oh, that makes more sense. I was like, wow. Okay. 13 is a nonlinear, so he's a little bit out there. Emma, did you do substitution or elimination? elimination? Okay, I think I would have too, because the plus y minus y is kind of nice. And I did tell you guys technically you couldn't, right? Even I know I'm prone to mistakes in that. I mean, you guys know that, it's obvious. But distributing that negative just to be safe. Oh, they need to do a negative. I just need to add down. Make it harder than it needs to be. There we go. So then that just cancels out. Naturally, I end up with x squared plus x squared, which is 2x squared minus 4x equals 0. How would I use factoring? Double checking with my graph seems to make sense. Then we just have to plug and check it back in. So then y equals 0 when it comes to 0. And 4? Yep. Oh, negative 4. Thanks. Gracias. I have to solve that by subtracting the others. And they match up respectively, so it has no 0, 0. That cool? If you had done substitution, it might have been a little bit harder. But hopefully you wouldn't have solved for x, solved for y for sure. Yes. Okay, anything else? Last call, 7172. All right, it's good and bad all at the same time. We're getting out of substitution and elimination and into what do we do if we have 3 equations? Some of homework will have 2. Oh, nope, he has 3. Nope, he has 3. He has 2. Oh, he has 3. Oh, and then there's another homework. Now, I think for some reason my homework numbers got a little off. Can you guys just double check in your homework spirals? Are we truly on 44? Okay. So it's going to look a little funny just because when we grade homework, I think either I split up a homework to be 2 that used to be 1, so it might not match up perfectly with the homework numbers up here in the documents, but it should be the same problems. I had to change the pre-cal homework problems. We're coming back into section 7.3, basically saying, cool, substitution, elimination, we get it. There are weird things like with quadratics and e to the x and like word problems with business and accounting and market equilibrium in econ. But section 7.3 now says that we don't just always stick with 2. What if we have 3? And you might be, well, I don't know. I don't know what your brain thinks of when you see X, Y, Z. So why don't you tell me? When you see X, Y, Z, just what's something that your brain starts thinking of? Alphabetical, sure, X, Y, Z. So X, Y, sure, why not a Z? What else? Graphs, what about graphs? If you have X, Y's, and Z's, what kind of graphs are you looking at? Oh, well, we could be thinking A, B, C, like X, Y, Z. So it could be triangles, but not in this context. How do you graph? Here's X, Y. How do you graph Z? Come out. Nikki, wasn't this you that brought this up the other day, the X, Y, Z coordinate system? Is that not you? Might have been Sophia. No, it was a while ago. It was like a week or 2. Maybe it was honors pre-cal. Sophia sits right there. Anyway, someone was asking about X, Y, Z and how to show a 3-dimensional graph. A 3-dimensional graph. Did you guys see the 3rd dimension in geometry a little bit? No? So wait, do you not even know how to graph something like 1, 2, 3? No one does? I mean, you gave me a quick head on. But no one else does? Huh. Interesting. Sorry, I'm still learning. I don't know. We had a lot of like switch over of math teachers there for a few years. So I'm still used to Mr. Shanks, who used to make his entire geometry classroom into like a huge XYZ plane. He would like have these huge axes just like everywhere. If you were trying to graph, well, it depends on how we do it. Let's do it the easy way. X and Y we're used to, yeah? Okay. Why is this dotted? What am I trying to show you? That it's out and back. Yeah? So then we'll make this one Z. Sometimes people say like X and Y has been put on the table and Z comes up. Like they sometimes make this Y and this Z, but for right now, we'll just make it X, Y. So if we were to graph an X and a Y and a Z, we would have to go to the right one, true? to the right one. We'd have to go up how many? 2. And then we'd have to go out 3. Now, is it hard to show on a whiteboard? Yes. Is it easy to show in like a box where you're like, oh, go this, and then this, and then this? It's right here, and like how are you gonna put a point in space? Maybe you should make it like one of those flower reservoir things. You can stick a stick pin in it. But anyway, it's a little bit confusing at that point. We can go over, we can go up, and we can go out, out, out. How do you show that up here? Over, up, out, out, out would be this distance. So it'd be right here. Which is weird and which is hard and which is complicated, but basically it's like over, up, and then out, and it's right here, but it's kind of shown as if you were looking at it two-dimensionally. Anyway, representing the third dimension two-dimensionally, I wish I was more artistic, it's great. That's not our point today, but just what I want to show you is when we're solving for things in this section, if it's a 3-system equation with 3 unknowns, if we were graphing it, we would be getting cool 3-dimensional figures. And with technology, man, we can like show it so much easier and like have a collection of points, be like this huge 3-dimensional object and all this cool stuff. But for us and for right now, we're not going to get back to the third dimension really until chapter 10 with conic sections, when we start spinning circles and ellipses and parabolas. But for right now, we're just going to say, you know what? You're going to get these answers that sometimes will have 3 solutions. And if you have no idea that this is really the third dimension, you might be like, I don't know what's going on. But the nice thing is you're not going to have to graph. You're not doing that. You're just going to be solving for who is X, who is Y, and who is Z. And to be honest, if we're talking about like business and econ, this might not even have like a graphical representation that anyone cares about. They might just be like, okay, we want to know we're making 3 different products. We want to know if these are our different constraints as far as like how many the machine can hold, or how fast the workers can go with the number of hours in the week, or how many the stores are asking of each type. Well, you might just be figuring out, okay, make this many boxes of that, this many boxes of that, this many boxes of that. Ooh, Girl Scouts, anybody out there? We could be trying to figure out, like, hey, the highest 3 in demand and how many to bring when we're going around the neighborhood. I don't know. But the idea is maybe it's not talking about 3-dimensional graphs. Maybe it's just talking about there are 3 things I'm solving for now instead of 3. And whenever we have 3 unknowns, how many equations do we need? 3. So maybe it has nothing to do with graphing, but if it was a graph, anyway. 3-dimensional graphing is tricky. It doesn't really come back tons until Prop 3 or vector physics. So, now that you at least know that there's a thing called Z and it's actually on a graph, let's actually talk about what we're supposed to be doing today, which is making something like that look like something like this so that our life is easier to get there. So over here. The same things that were allowed in elimination are allowed now. We're allowed to change. We're humans. We're creative. We're not computers. We like things to be nice and neat and organized. But we don't have to do it the same way every single time because we're not necessarily having to run on programs. But we need it to be legal. So if we want to switch things up, we can change the order of equations. If we don't like the top one being the top one, if we don't like the top one being the top one, we can change these two and say, whatever, I'm making here the top one. The second one can be the first, or the third can be the second. Or we can just make the second and third switch. We can switch around if it would make it easier on your brain. We can multiply whole equations by constants like we saw with elimination. We can add, subtract, but I'm going to say add or add the opposite because once again, we all make mistakes. And those seals, man, way too many die. But I say chain gang is the stair-step system. Chains. What's true about chains? Why did I use chains? What are chains comprised of? Links. How good is the chain? Only as good as the links. Now, yes, we can use the material and how thick the links are, etc., etc., etc. But the chain is really only as good as the strength of the links that are being held together, right? This is a stupid example, but I have traveled a few different places. And keychains. Love the keychains when they're super unique to like the region that I'm from. Not that I like carry them all, but love the keychains. Hate the keychains when I'm like walking my dog and he pulls me and then the main keychain itself and then there's like that little metal piece that then holds the really cool thing that links on. So many of them just fall apart and I'm like, seriously? Like it's not necessarily the keychain that's the problem, it's like that little interlocking piece. Or even like some of you guys with necklaces or earrings, sometimes that gets pulled apart. Or even like when my dog with his dog tag, like sometimes if he pulls too hard and it was on the wrong part of the collar, then it like pulled out his whole name tag. A chain is only as good as the strength of the links. Now, why am I saying chains? Because I just need you guys to realize there is a very clear system that we are going to follow. We're trying to figure out, in somewhat getting towards, once again, that computer programming way of looking at a problem. I know if I was just to throw this on a Post-it on your desk yesterday and say, do whatever you can to solve for X, Y, Z, I know some of you would have gotten there, but the problem is, I think that out of this entire class, out of those of you guys that would have gotten there, we would have had probably at least 3 to 4 to 5 different ways of how you got there. Right? Like that makes sense. Some people would choose to be like, oh, I'm going to take those two, and I'm going to take those two, or I'm going to take these two and cancel, and then what's the problem if we're a class of 30-ish kids, a little bit less, and we all solve a problem a different way? Why is that dangerous? Huh? Yeah. What if Sid makes a mistake doing her way and no one else is doing it that way? Think homework questions, if nothing else. Think homework questions. I couldn't make it match. How'd you do it? Oh, you did it that way? Everyone else did it a different way. Does that make sense? Like, as far as a class and trying to get to a solution together, or as far as a test and trying to solve the long answers together, not together, because you're working separately, but just think about my answer key. If I do it one way and all of you guys do it like all your unique creative ways, do you just see like logistically how that can be hard to find your mistake in your approach? Does that make sense? And we just talked about how with like section 7172, how many of you guys made at least one dumb math mistake? Oh, the rest of you guys, party poopers, and then thank you. I did up here on the board. If nothing else, how many of you guys saw someone make a mistake? Okay, half of you don't watch me. 3/4 of you don't watch me. I made mistakes. So mental math stuff is going to happen. If mental math stuff is going to happen, if we could all be following the same system, we'll be able to find each other's mistakes at the same place. Not the same places, but where they occur, when they occur. If nothing else for homework questions, and if nothing else for being able to, if you get stuck, allow me and the rest of the class to help you. So along those lines. Partially, we're getting ready for computer programming and thinking about like a system, a procedure that could always work. Getting that direction, but still being able to be creative humans and kind of make life easier for ourselves. But realizing we're all going to be solving these problems together, and so to find mistakes, we need to at least somewhat have a similar approach. Here's the approach that you're going to do, or that I'm telling you to do, if you're awake. First two. We're going to name this one Equation 1, Equation 2, Equation 3. When we get into matrices, it's actually called R1, R2, R3, whatever. Row 1, row 2, row 3, or equation 1, equation 2, equation 3. The system says the following. We are going to eliminate x terms in 1 and 2 and 2 and 3. This should feel very much like I'm giving you a program to follow. We're going to do elimination, eliminating the x's in 1 and 2 and 2 and 3. So as you guys see me over here doing elimination in 1 and 2, we are humans. We don't necessarily have to do that weird like dividing or multiplying both by each other like Nathan brought up the other day to make it cancel. We get to look at it and say, oh, this is easy. What's going to make these two eliminate, guys? Addition, simple addition. So I'm going to do equation 1 plus equation 2. So equation 1 plus equation 2, we could write it all out, and for sake of illustration in this one, I will. I'm a lazy person, though. If I was doing this on my paper, I would just do it in my head and get that new equation. But since I'm trying to show it and model it for the rest of you guys, I'm going to write it out and actually do that addition, showing the step itself. So when I add, I'll end up with those x's eliminating just like I needed them to. I'm going to end up with y plus 3z is equal to, double check my math, if we're all doing the same system, we should all be at the same next step, right? Perfect. Guess what? That's equation 4. And it will always be. So we're getting equation 4 from this one. We're going to get equation 5 from the other one. We're going to go ahead and do the exact same thing. Well, not the exact same thing, but the exact same objective of eliminating the x's in 2 and 3. But in this one, can I just add the 2 together? No. Now, if I was a programmer right now, I'd be like, oh, stink. So sometimes you're adding, sometimes you're not. What can I do to both equations to make sure these always match, and then I can always add, and then it will always eliminate. But we're humans, and we're like, no big deal. Multiply the top one by. So we multiply the top one by 2. I'm going to say equation 2 needs to be multiplied by 2, and then I'm adding it to equation 3. We're humans, we can have this change every time. Computers would need it to be the same every time. But some of you might be thinking of Nathan's trick the other day, that if you multiply one by the other and the other by the one but opposite, it will always be able to be added. Anyways, I'm going to go ahead and multiply that second one, every one by 2, because this is where mental math will start to break down if you're trying to do too many things at once. I'm not saying I wouldn't do it, I'm just saying it's dangerous. So now as we go, those x's cancel. Why? Because I made it that way. Why? Because we're trying to eliminate them. Okay. Y plus 5z equals. We're all doing the same system. We should all be at the same next step. I now have equation 5, and I have equation 4. But what's true about equation 5 and equation 4 if I've done my first step right? The only variables they have will be y and z. So right away, Nathaniel, I'm at that second row of my row echelon form of having eliminated one of the variables. Now it's time to go eliminate the next step. I got rid of x's, that's awesome. Now it's time to get rid of, you see it? Let's get rid of those y's. We're going to eliminate y's in 4 and 5. I'm not programming. You guys are human, so I can say, sweet, look at it and make it work. The computer would have to figure out how to tell it a system that would always work. But you guys, look at 4 and look at 5. What can we do in order to get rid of those y's? Yeah, we can multiply by a -1. We could subtract, but distributing that negative will be much safer. So we could go ahead and do negative first equation. Not first equation. Who are we putting together? 4 and 5. So we're going to do negative equation 4 plus equation 5. Sure, why not? So that'd be negative y minus 3z equals -5. And then we have y plus 5z equals 9. Now guys, if I was the book, you guys have seen them on CalcChat, I'd be writing like whole paragraphs of this book, right? Like not just doing like little circles to mean the equations. That's confusing. If you were actually writing this out, there'd be tons of words, but we got this. So if we add down, the y's are gone. Negative 3z plus 5z is 2z equals 4. Z is equal to 2. Why did I go there? Because I just got my equation 6. That's our last step. Solve for z equal a, and then technically we're just going to go ahead and set up our row echelon form. Now, if we weren't humans, computers would actually need to know who to put in. But for you guys, we're just going to go ahead and pick one of the original equations that has an x, y, z. Some sort of x, some sort of y, some sort of z. We're going to pick either equation 4 or 5. Both of them should have a y and a z. And then all we got to do is throw in equation 6. If you did it right. You might have a number in front of Z, but if you follow the system, I shouldn't put E. That's 2.7188. We'll make it back. Bless you. But at this point, we have our stair step. And the reason that you guys wanted the stair step was because he's easy to solve. So at this point, we could just go ahead and let's get rid of that. Oh, I'm saving. That's helpful. Not really. Still not helpful. There we go. I can have exactly what I want. X minus 2y plus 3z equals 9. Y plus 3z equals 5. Z equals 2. My mental mathers. You'll probably just be plugging in your head and saying, hey, that's 6. 5 minus 6 is negative 1. And hey, that's a lot to keep track of, but I got it. That's going to be a negative 1. That's going to be a 2. So I have 6 plus 2 is 8, and I subtract. That's a 1. My non-mental mathers, no stress. Take your time. Safe rather than sorry. So I have 3 plus z times 2 equals 5. Solve. And then I have x minus 2 times what y ends up being. Solve. And we have x, we have y, we have z. Now, why in some ways am I not bothered that the bell is about to ring in 60 seconds? Don't just like stress me. Why am I not stressed? What did I say about this homework? Well, it's only half of it. And what did I just show you if I talked about how, like, hey guys, a lot of these are going to have 3 different equations. This is a system. What is a system meant to be used for? Organization. But if this is a systematic approach to this problem, isn't it only a good system if it'll work for all of them? Right? So, what's the system? I don't know. Always take the first 2, get rid of x, you'll always get y and z. Take the second 2, get rid of x, you'll always get y and z. Take those 2, that'll always have y and z, and get rid of y's. Will this always work? Yes. Follow the system, but wait, hold on. Some of you were like, no. Weird stuff happened in 7.1 and 7.2. When did it get weird? When more word problems, but also you're not going to see those tonight. No word problems tonight, but also when do you remember what was weird? When everything cancels. Okay, could everything still cancel? Yes, and we'll talk about what to do with that tomorrow. You might see it in one of your problems in homework.